Okay, we're going to use this to replace the lab that we missed because I was sick. So let's go ahead and get started. We'll go ahead and talk about recrystallization first and then melting point. But before we get into any of that, let's make sure we're all on the same page as far as bonds, intermolecular forces, all that fun stuff. Okay. So one of the things that you guys should know in theory by this point is how to rank or classify different molecules or different bonds based on these three main categories. And ideally, you see a structure and you're able to come up with this. So we talked about this briefly when we did the solubility lab, but just in case you forgot. When it comes to ionic bonds, so what we could look for ionic bonds is a metal bound to a nonmetal, or if we see charges. Okay, it may be an and case too, but if we see metals and nonmetals or charges, i.e. the plus or minus, sometimes you'll see them together, we know we've got an ionic bond. So in the case of this molecule over here, we can see an ionic bond there. Okay, covalent bonds are equal sharing of electrons, and that's where this gets a little bit whatever. We're looking at equal sharing of electrons. So if something is bound to itself, so anything bound to itself counts as a covalent bond, or in some classifications, nonpolar covalent. That's a bit of a narrow definition, so we expand it slightly to include carbons bound to hydrogens. Okay, so really those are the only two cases that we'll see this semester where you could see covalent bonds. So if we go back to our molecule, pretty much all of this is going to be a covalent bond structure. And remember, we have hydrogens in there as well. Okay. And then what I would typically say is the more difficult one is your polar covalent bonds, which pretty much covers the rest of it. Okay. As a general rule of thumb, I would recommend that you remember anything bound to an electronegative element, but because this is organic chemistry, we can simplify that. Instead of anything bound to electronegative, we can say anything bound to oxygen, nitrogen, or a halogen. Okay, so if we go back to our drawing over here, we've got that carbon-oxygen double bond, and technically that carbon-oxygen single bond. Okay, these definitions are not 100% correct. These bond classifications are strictly based on differences in electronegativities, but if you run, most people don't know the electronegativities for all the elements. Further, if you base it strictly on that, a lot of the reactivity kind of falls through the cracks. Okay, so these definitions, while kind of vague and broad, allow you to determine different reactivities or foresee different reactivities further on down the semester. Okay, so what can we do once we know the type of bonds? Well, that's where we can get into our intermolecular forces. So if we started with an ionic bond, I'm pretty sure we already saw all this, so we'll go through it kind of fast. If we started with a structure that was ionic in nature, that means we've got this negative positive. How does it interact with other molecules, particularly like molecules? So when we talked about this before, we either have this top interaction or this bottom interaction. And as you might, in theory, be able to predict, we would expect the top interaction, in this case, to be dominant. And that's because we get this negative-positive canceling out. Okay, so almost all organic chemistry is based around this negative-positive canceling as best we can. Okay, the next one that I would say is a little bit trickier that falls out of that pattern would be looking at the carbon-hydrogen bond, okay, which we've decided was covalent, which means equal sharing of electrons, which means there isn't really a charge associated with these. Okay, which brings up the next issue: which interaction then is favored? Well, if we don't really have this cancellation of charge, really neither is favored. So we end up with a different type of intermolecular force. Okay? So when we're looking at a covalent structure, we're looking at London dispersion forces. When we've got a ionic structure, you'll see it typically referred to as ionic forces, sometimes as electrostatic. And when we move to the polar covalent bonds, which we've got shown on the right as possible examples, this is where we get dipole-dipole forces. The special exception to that would be if you have a hydrogen bound to oxygen or nitrogen, you also get hydrogen bonding, which is this last interaction here, hydrogen bonding. Okay, so we've got pretty much three primary forces with a fourth extra one just because it's a special case of dipole-dipole. It's these intermolecular forces that determine a lot of the physical properties. And we looked at that when we looked at solubilities, trying to predict the solubilities of different compounds. So we tried to kind of guess and check as we went through that. So what we can then do is take this a bit further, or summarize it in this picture on the left. And the idea here is that we use this color wheel to interpret the different intermolecular forces. So if you look at a structure and see primarily just covalent bonds, you would expect London dispersion forces. If you've got primarily polar covalent bonds, then we would expect dipole-dipole forces as our strongest force. Okay? And then lastly, of course, if you got ionic bonding, we would expect ionic forces. Okay? There is some extra information stashed in here. For instance, we get a strength of interaction. Okay? This strength of interaction would technically actually push all the way around here. Okay? A London dispersion force is an incredibly weak interaction. Okay? And in comparison to an ionic force, it's incredibly weak. So our ionic force, because we're neutralizing those partial charges, is going to require more energy to break apart. But then I said it continues around. Okay, and this is where I think a lot of misconceptions can occur, and easily done, comparing a covalent bond to an ionic bond. Okay, I would make the argument that a covalent bond is typically stronger than an ionic bond. Okay, why would I suggest that? Well, let's think, I'm actually not positive on this one, but I think I'm correct. Let's take the melting point of diamond versus salt. Okay, we haven't really seen liquid diamonds anywhere, but we can get liquid salt. Why? It's because the ionic bond is a little bit weaker. Okay, the covalent bond is inherently strong. So where's the misconception? Well, if I take a typically covalent molecule, say carbon dioxide, and a typically ionic compound, say sodium chloride, and we look and compare their melting points. Well, when I compare the melting point, I say, well, carbon dioxide has a much lower melting point than salt. So that must mean its bonds are weaker. We aren't comparing bonds at that case, though. What we're really comparing is the forces. And in the case of carbon dioxide, we're comparing London dispersion forces to ionic forces. Well, in that case, your London dispersion forces are weaker. We would predict that the boiling point would be much lower. Okay, so it's tricky trying to separate the two. Okay, bonds are not forces, forces are not bonds. They're related to each other, but try to avoid mixing them, if that makes sense. Okay, so if we were going to use this to predict melting points, we could compare, say, water and methane. And if we look at the LDF force, or our intermolecular forces for methane, we would probably run with London dispersion forces. With water, we get hydrogen bonding. Well, between those two, which one's the strongest force? Hydrogen bonding. That means it's going to require more energy to break it away from other water molecules than CH4 from itself, which would mean the higher melting point will go to water. Okay, so if we look at their physical states, water is a liquid, methane is a gas at room temperature. So clearly our observation holds true. Okay. We could push this further with methane versus ethane. We get the same type of intermolecular forces, LDF, in both cases. But now ethane has the edge over methane because ethane has more London dispersion forces. There's 2 carbons, if you will, versus 1 carbon that allows for those intermolecular forces. Okay? So what we're applying is these intermolecular forces and how they relate to each other and see what we can do with them. Okay? And that's where we get melting points, which is ultimately what we're going to look at the end of today. We're also going to take advantage of this in conjunction with solubility from however many weeks ago that was, 4 or 5 weeks, to come up with a way to purify. And that's going to be our crystallization technique. Okay? So let's go ahead and summarize what we remembered from our solubility. So we would rank things based on the strongest force first, if we're going to look at our solubilities. But then we could also push to amount. Okay, so we really had 2 primary stages that we could look at. For instance, when we look at dodecanol's solubility in water, we would expect them to not be soluble, even though the strongest force in both cases is hydrogen bonding, but there's a vast excess or a much larger amount of intermolecular of London dispersion forces coming from dodecanol. Okay, so the amount there overwhelms our strongest force. Okay, we could take it further and look at similar total intermolecular forces. If you think back to the solubility experiment, methanol and salicylic acid. Okay, those 2 should have mixed. And if we said hydrogen bonding was the reason why, then when we take salicylic acid and put it into water, we would expect them to mix too. And they didn't. Okay, so it's the characteristic of methanol that it has both the London dispersion forces and the hydrogen bonding that really kind of pushes the solubility over the top. Okay, and the last one was the structural considerations. That was ultimately, if you compare the solubility of THF, diethyl ether, and water. Okay, so I'm pretty sure we talked about that fairly extensively, so I'm just kind of reminding you of that, and I don't want to get into it right now, because it's a bit excessive. Okay, so what can we do with all of this? Well, what we're going to try and do is purify a sample, so that's our ultimate goal. So we're going to start with an impure sample, and in this case I'm picking circles and squares. And you'll notice that this impure sample has some interesting characteristics about it. You'll notice that it doesn't completely stack neatly. So if we go in and look at those squares, they're not perfectly aligned. This one's a little bit off skew. Everything's kind of shifted, and that's due to this impurity messing with how that crystal stacks together. Okay, and we're going to talk about how we can figure out that at the very end of this. So ultimately, first we need to come up with a way to purify and separate this. Okay, so we could go based on melting points. So what we could do is physically heat everything up to a ridiculous temperature so that all of these species are completely independent and away from each other, and then slowly cool it back down in the hopes that we would just get the squares interacting with each other and just the circles interacting with each other. Okay, that's a bit difficult to do, but it's not a bad idea. Okay, and we'd end up with our pure substance. Okay, and since I don't remember the next slide, let's take a look. So we have to break everything apart, try and get that to actually occur. Okay, where our issue comes into play largely comes down to what field we're working in. We're dealing with organic molecules, and so an undergraduate lab. Heating it up to that kind of temperature would mean having to push into a gas phase. In an undergraduate lab, we really want to avoid the gas phase because it's not the easiest thing to work with. all sorts of hazards, particularly if they're toxic chemicals. We don't really want to run the risk of you inhaling some of these dangerous things. Okay, so that's a bit sketchy to deal with, but hey, sometimes we're exciting. We'll go ahead and do it anyway. The next and potentially bigger issue is that, sorry, just lost my train of thought, is that organic molecules have some heat issues, to put it mildly. Okay, think about it this way. We're made out of organic compounds. Our t-shirts, our clothes are all made out of organic compounds. What happens when we heat them up? Do we really see them turn into a liquid? Or do they melt or combust, or do they burn, combust, turn into CO2? Okay. We typically see decomposition of organic molecules when we heat them up enough to try and push them into the gas phase. Okay, so it's not really the best option to try and purify something, particularly if you spent hours and hours trying to get it isolated, to turn it into the gas phase. Okay, so we need to come up with another way to go about doing this. Okay, and what we're going to try and do is take advantage of the polarity of those molecules, and in particular, their solubility. Okay, this one gets a bit interesting. So what we'll do is add a third substance. Okay, and what we'd hope, or in some situations what we would hope, is that this third substance would interact with only one of those particles. Okay, so what we'd be doing is seeing is it dissolve. That's great. One's now dissolved into solution, the other one stays a solid. Can I separate a liquid from a solid? Sure, why not? I could filter. Okay, so that could work out pretty well. Okay, it's still technically going to be impure at this stage, hence you've seen me, or you see the, whoops, sorry, I wasn't supposed to quite do that yet. Hence you see it marked as impure there, and we would purify it by filtration, okay, to separate the solid from the liquid. Okay, what's an example of this kind of trivial separation? Well, if I had a mixture of sand and water, or sorry, sand and salt, okay, to purify those or to separate those two compounds, we could physically do it. That's a bit tedious. Or what we could do is add water. So we add that third substance, water. Water interacts with the salt, but not with the sand. Okay, so then the salt dissolves in the water, sand doesn't, and I can filter out the sand, and I'd be left with a saltwater solution or the sand. Depending on what I wanted to do, I could then either isolate the sand already or isolate the salt by evaporating off the water. Okay, so that's nice, except we're not in a perfect situation like that. Okay, let's say that instead of it completely separating like that, we go back to our impure starting section here. We say to get this salt molecule out, so if we call that one our salt, and our blocks our sand, to get that individual salt molecule out, what do I have to do? I have to physically remove each of these pieces. Okay? Once they're out of the way, then my water molecules can come in and grab a hold of the salt and pull it out and into solution. Well, how do we do that with the sand and the salt? Well, we could mix it. That'll work. Stir it around really well. Try and get those layers to mix as much as possible. But let's be really, really ornery here. And let's say that this is what I've got. Okay? So here's my my sand block. Okay? So it's solid sand all the way around that. And there's my salt molecule right in the middle. How do I get that salt molecule out? Okay? Everyone likes to suggest grinding. That's not a bad idea, except I'm being even more ornery than that. Can't grind to get that salt, get the sand broken up. That's the smallest that we can physically break it into. How do we get the salt molecule out? There's the problem. We can't. So this system, while it works or illustrates nicely what's going on with kind of a trivial situation, doesn't work so well for our system as far as organic chemistry goes. Okay, because we aren't going to be able to finally grind our samples enough to be able to get those impurities out of our crystal lattice. Okay, so what we're going to do in our difficult separation is we're going to try and take advantage of something else. Our solute, our solvent must be able to dissolve everything. Okay, so it's got to be able to come in and pull each of those molecules out away from each other entirely. Okay, once they're all separated, we then need to be able to somehow change our system such that our crystals form, and we end up again with that preferred state. Whoops, sorry. So that gets a bit tricky. Okay, what can we do in these stages to control that dissolving process? Okay, well, remember our very first attempt at trying to separate these things was to heat them up. As we heated them up, we break down those intermolecular forces, holding those individual molecules attached to each other. Okay, so what happens if I add heat and add solvent? Okay, well, now I'm providing two ways to break down those intermolecular forces. So what I'm hoping is that my compound, my target compound, in this case the blue squares, will only really dissolve once I add heat to help kind of break everything apart. Okay, so then it's all dissolved. Now if I had that, remember back to our initial issue, if I had that impurity in there, my solvent's been able to break everything apart in conjunction with the heat. So now I can get that impurity out. Okay, but my goal is I still need crystals. Okay, well, the hope, or my choice, is that I'm going to then cool everything down. Okay, and ideally the solvent that I've picked to dissolve initially, okay, will only dissolve when I've added heat. Will only dissolve my compound when I've added heat. So what happens when I cool it down? Now it starts to say, well, I don't want to be dissolved anymore, so it starts to crystallize and in theory not precipitate, but crystallize out of solution and form solid. Okay, so our hope is that as we cool, we can selectively and slowly cause our product to crystallize out of solution. Okay, if we do it too quickly, then those crystals all jump to each other or grab a hold of each other, and they trap impurities in between. Okay, like the solvent molecules. So what we want to do is let this process happen very, very slowly. Excuse me. And the hope is that we can get our purified product at the end. Okay, and in theory, our impurities would stay dissolved in our solvent. Okay, and we'll talk about a few issues with that in a second. Okay. So, some observations with solubility. Okay, there are some assumptions that we're going to end up making. Okay, our first assumption is that our solutes will dissolve independent of the other in the presence of other solutes. Okay, so if we use this table to the right, at 0 degrees Celsius, we'd be able to get 7 molecules to dissolve in 100 milliliters of solvent. Okay. So if I start with 100 milliliters of solvent and I add stars to it, 5 dissolve. Okay, let's say I add 20 stars to it. 5 dissolve, 15 don't. Okay, now I add the dots to it. 2 dots will still dissolve. Okay, so the stars and the dots interact with the solvent independent of each other. Okay, which isn't always true, but for our purposes and what we're going to be dealing with, that's a fairly accurate statement to make. The next assumption that we're going to make is that solubility has a very strong and direct relationship to temperature. As we increase the temperature, we increase solubility. We already discussed why that might be important. Temperature breaks intermolecular forces. Hence, when we move from a solid to a liquid to a gas. Solubility is doing the same thing. It's breaking intermolecular forces in favor for interacting with the solvent instead. Okay, so it makes sense that our solubility is related to temperature. Okay, so those are some two primary features that we're going to have to take or use in the process of recrystallizing. Okay, so the next thing, put it all down into a graph to make sure that we understand what's happening with solubility. Okay, so before we actually start interpreting the graph, we're going to do what might be considered a bit silly. Okay, I want you to think about and label your graph with the obvious information first. Okay, so what's that obvious information? Well, see the little red dot there? What can you tell me about that red dot? Okay, low solubility, not a bad idea, except I'm not on the solubility curve. I'm only on the temperature curve. Okay, so let's look at the temperature. Temperature's increasing in that direction. That's probably a high temperature. Or if we want to get really scientific with it, we can call it hot. Okay, just like Paris Hilton. How about the blue dot? What can you tell me about that blue dot now? Good, getting the hang of it, call it cold. If we move to our solubility line, our blue dot now on the solubility line, low solubility, because it's low on our line, also known as insoluble. And we can also push to the top of our curve, and we can say high solubility or just soluble. Okay, if we want to get special, we can call it high too, or highly, because I guess it's a adverb, something like that. Okay, so now let's take a look at the possible options on what things could show up in our graph. Okay, and that's what we're summarizing over here. So let's take a look at something that is always insoluble. Insoluble things tend to be black and dead, right? So let's go ahead and call that black. Okay, what would something be that's always insoluble? Okay, well, at cold temperatures, where should it be? Good call. It should be nice and low on our graph. Come on, show a little point there. Still attempting to show a point. Okay, and what about hot temperatures? Well, if it's always insoluble, it doesn't matter what temperature it is, so probably run always insoluble. What we would expect is a line running virtually flat, right, really, really low on our curve. Okay, what if it was highly soluble? So let's go ahead and pick something red. Okay, something that's always soluble. Well, at cold temperatures, we would expect it to be highly soluble, and at hot temperatures, same deal, highly soluble. Okay, and what we're trying to represent here are the ideal cases. Okay, most things increase with solubility, or increase with solubility with temperature. So we would expect a slight line on this, but what we're trying to do is exaggerate those issues. Okay, what if something was soluble at high temperatures only? So now we'll draw on a little purple line. So we can say hot and highly soluble. We're looking at something probably there. That's only one data point. Where's the other data point? Okay, well, the curve did, or our statement actually implied something else. If it's soluble at high temperatures only, that means at cold temperatures, it needs to be insoluble. So we'd be looking at something running vertical, okay, or on that diagonal. Okay. Lastly, we could go ahead, let's go ahead and do this. Draw on our green dot, something soluble at only low temperatures. So I don't want it to crowd out our thing too much. I'm just going to draw a dotted line. Does it really make sense for something to be soluble at low temperatures only? Well, probably not, considering that as we add heat, we break intermolecular forces. So solubility breaks intermolecular forces. You add solvent and heat, it should really actually increase in solubility. There can always be exceptions, but that's primarily going to hold true. Okay, that really doesn't make sense. So let's add some more terms to this to try and figure out what each of these things mean. Okay, so what if which of these things would be our target compound? Well, if you flip back to those previous boxes and circles and all that fun stuff, we wanted our compound to have a varying solubility. It needed to be soluble at high temperatures and insoluble at low temperatures so that we could filter it out. Okay? So that would be our target compound. Which of these curves matches that line? Okay, well, there's only two that vary with temperature. We said the green one doesn't work, so it's got to be our purple one. So that would be our target compound, what we would want to happen. Okay, or our target solvent, our ideal target solvent relationship. What about the other two curves? Okay, the red and the black. Well, the red one is highly soluble, so this would be an ideal soluble impurity. For instance, if we added, say, salt to it and we just try to dissolve it in water. Water will dissolve our salt at all temperatures. It makes sense for that to be our ideal soluble impurity. And then the last one would be our ideal insoluble impurity. Okay? One that's more common than not is sand. Sand tends to show up in a lot of products or purifications coming from organic chemistry because we use it in other techniques that we'll see this semester. Okay? So that's kind of the idea on where things are on our curve. And so if we were going to try to purify a target compound, okay, so let's look at some possible options now of what we might try and get rid of. Let's say our target compound was mixed with a soluble impurity. Okay, how would I get rid of that soluble impurity? Okay, so what I need to do is find the point at where my target compound and the soluble impurity have different solubilities. So I can go to hot temperatures, and if I go to hot temperatures, what do I notice? They have the same solubility. So if I try to dissolve the target compound at hot temperatures, the impurity dissolves, target dissolves, no way to separate them. Okay, we can't separate a clear solution. So what we can do then is say, okay, well, what happens if I move to cold temperatures now? So at cold temperatures, my soluble impurity and my target compound have drastically different solubilities. Okay? So now I could separate them. My soluble impurity stays dissolved, whereas the target is a crystal. Okay? It's insoluble. So how would I separate those two from each other? Whoops. Okay? You might have guessed one option or one description of it. We could filter, okay, to get the solid away from a liquid. But I'm going to say that's not quite accurate enough. I want to add a little bit more detail to that. We need to do a cold filtration. Okay, because if it was hot, it wouldn't work. So we need that extra piece of information as far as our procedure goes. Okay? What happens if instead of that mixture, I had a mixture of the insoluble impurity and the target compound? Well, if we went and looked at cold temperatures, say, hey, it worked once, why not do it again? We'd notice that our target compound and our insoluble impurity are both very low solubilities, which would mean when I add my solvent, neither one dissolves. I can't separate them. Okay? So what I need to do is change the temperature. Okay, in this case, let's go ahead and heat it up. What happens when I heat it up? Now when I look at my target compound solubility versus my impurity, different solubilities. So now I could go through and separate them. Okay, and what would I need to do to separate it then? Again, it's a filtration, okay, or filter, because that's what I've been using. We'll go ahead and stick with filter. But if it was a cold filtration, it wouldn't work. I have to make it a hot filtration. Okay, So the idea with a lot of our crystallization steps and purification schemes as far as this goes is manipulating this graph and trying to decide where different phases are, how we can separate them at each stage. Okay, so it's a little bit tricky to get through. Last summary, just to kind of narrow or hopefully summarize everything. If we're going to look for our target compound, we want to find the ideal solvent. Okay, what do we hope to see? Well, at cold temperatures, what do I expect? It better be insoluble. So I could filter it out. I could do a cold filtration and remove soluble impurities. Okay, at hot temperatures, it better be soluble. That way I could remove my insoluble impurities. So we're really relying on that difference in solubility to purify these ideal impurities. Okay, I know there's a lot on this curve. It's a lot to deal with because it's a lot of new information, but I'm going to go ahead and make it even more difficult. What happens if our impurity happens to be this blue line? Okay, I'm going to give it a special name here. I'm going to give it the soul impurity. Okay, why the soul impurity? Well, because it's going to steal your soul if you get too much of it in there. If you get an impurity that matches your target compound solubility, you run into some issues with being able to purify. Okay, because you heat it up, they both dissolve. You cool it down, they both precipitate. Really, the only way that you can remove the soul impurity is if there's very small amounts. Okay, and even then, you end up losing your target compound in the process of purifying. Okay, so if you've got a small amount of impurities, recrystallization works great. If you got a lot, we'll need a new technique. We'll talk about that hopefully next week, assuming I'm not sick. Okay, so a lot of information went into that. Hopefully you can kind of process it, slow the video down, re-listen to different aspects of it, and put that all together, and then ask me tons of questions next week. Okay. But lucky you, that's not everything. Okay. Once we've gone through and done this process, we need to prove that you actually purified the compound. Okay, and that's the optimistic side. The pessimistic side is that you need to prove that you should have done all that work to begin with, because why bother to recrystallize when you lose product if it's already pure? Okay, so what we need to do is come up with some kind of technique that allows us to identify if a compound is pure or not. Okay, or even further identify what it actually is, and that's where we move to melting points. Okay, melting points are pretty nice because they are consistent for a given compound. There's a very small change in volume as you move from a solid to a liquid, so it's not pressure dependent, which means that no matter where you are on the planet, the melting point of a compound is relatively constant. Okay, so we can use the value of the melting point to identify a compound. Okay, so that's a pretty big benefit. Okay, the next thing that we can do is use it to establish purity. Okay, so whenever you write a report from here on out, almost all of your reports are going to involve obtaining a melting point. Okay, well, when you obtain a melting point, you should be giving me two pieces of information in your discussion and conclusion. One, that you were able to identify what the compound was, and that two, you now know that your compound was pure. Okay, it's really, really important to be making those conclusions and making those conclusions separate from each other, because they're based on different pieces of data. Okay, and we'll take a look at those here in a second. So let's take a look at a pure compound. Since I like boxes, we'll stick with boxes. Okay, what phase are we looking at here? Okay, of our pure compound. What phase would this be? Okay, as a big hint, we could go through and say, might look something like this in a different phase. And then it might look something more like this in the last phase. Okay, what are we looking at? We're probably looking at a solid. How do we know it's a solid? It's stacked, it's organized. Yeah, so we're looking at a solid. So what keeps it a solid? Okay, well, what do those lines represent? What's happening at each of those interfaces? It's the intermolecular forces between each molecule attracting to the other molecules. Okay, it's in a very regular, organized pattern. Okay, so that's ultimately what's keeping something a solid. It's those tight forces. Without those forces, you don't have a solid. Okay, so when we change the intermolecular forces, we change the melting point, and we looked at water versus methane or water versus CO2. Okay, so you should be able to get a rough idea of the melting point based on the intermolecular forces of the compound. You expect it to be really big, really, really small, depending on what forces you see. Okay. So now the next part. If I want to remove a molecule, I want to remove this molecule in the corner. Let's go ahead and switch to a slightly darker blue so it stands out. Remove that molecule versus this corner molecule. Okay. Well, how much energy is it going to take to break that molecule out of there? I know that's kind of a weird question, but let's just pick a number. Let's say anywhere between 1 and 10. I'm going to guess that you said 12. Okay, I can accept that. It requires 12 energy units to remove that molecule out of there. Well, how much energy does it take to remove that one? Exact same forces, which means the exact same energy units. Okay, well, how are we going to monitor that energy unit? That's going to be with temperature. Okay, so if we're going to look at an ideal pure compound, all the intermolecular forces within that compound are the same. So when I hit the threshold of temperature that it clears that energy barrier, I'm going to transfer from a solid to a liquid at an instant. Okay, so it's going to happen really, really quickly. However, if we look at this solid, would we expect this molecule in the middle to have that same energy? Okay, probably not. It's going to be slightly different because I'm going to have to break away the outer one first, and then, or several of the outer ones first before I can get into that inner one. Okay, so when we look at a melting point, the melting point is never really a point. It's a range. Okay, so it's the range of the temperature from when it starts to melt to when it's completely melted. Okay, and that's not the easiest thing to see. Okay, so when we're looking at a pure compound, what we would expect is our melting point would be very close to the literature value for that compound. This is the same compound. And then we would also expect the range to be fairly narrow. Okay, and narrow is kind of an arbitrary term. In general, most people seem to accept less than 2 degrees Celsius being a narrow range. I'm a bit more pessimistic, and I usually pop it up to about 5 degrees Celsius for being a pure sample. Okay, and it varies from compound to compound and professor to professor on what they expect. Okay, so those are our two observables. Close to the literature, I can identify the compound. Narrow range means it's pure. Okay, so let's push the threshold on this. Let's see what happens when we have an impurity. Okay, well, when we add the pink trapezoids to this, what happens to the crystal lattice? Okay, well, what ends up popping up here in the middle, which I'm probably going to now color in black? Okay, what is all this space? Okay, it's exactly that. It's empty space. Okay, what's happening in that space? Nothing. No intermolecular forces. Which means if I go through and look at the energy to remove this molecule, it's probably close to that 12E that we talked about before, okay, for the pure compound. But if I go over here and look at this one, not going to be 12E anymore because I've got that empty space. Okay, that empty space means the energy's dropped. I might expect, say, 9E. What about for this molecule that has even more space? Well, we might be dropping even lower down into, let's say, 6E. Okay? The numbers aren't critical, but what is important to notice is that our range, or our value, our literature value of when it starts to melt is going to be substantially lower because I've disrupted that neat crystal lattice. Okay, the next big issue is if I look at the range over which I melted, it was from 6 to 9 to 12 energy units. So now instead of being in a narrow range, I'm spread over a much larger range to cause the compound to melt. Okay? So when I have an impure compound, I typically expect it to melt at a temperature lower than the literature value. Okay? And that's just due to how the impurity disrupts the crystal lattice. And then I also expect the range over which it melts to be much, much broader. Okay? And that's typically where I would go with that greater than 5 degrees Celsius. Okay? That's why I liked the less than 5 degrees before. Okay? So deciding where that range is, okay, that gets a bit tricky to try and nail down on when it's actually started. Okay? Your range, I mean, we could pick it out real simply and just say, well, it's when it starts to melt to when it actually melts, or when it's fully melted. Well, fully melted is pretty easy. It looks like a liquid. When it starts to melt, it can actually be a bit tricky. And really, it just requires a bit of experience watching different compounds melt to figure that out. Okay? But I can step it up and help you out a little bit with that. On top of this video, I would recommend that you watch the melting point video, okay, which is found under the, I believe it's Organic Lab Techniques. Okay, that video will explain a lot more. I don't know how to spell techniques. Whatever. Here, let's fix it. There we go. Organic Techniques. That video will explain a lot more detail what's going on with melting point. It also shows you the experimental, how to do it, put it all together. Okay, so I would highly recommend that video, particularly because you guys didn't get to run the melting point this week. You will get to run it, however, next week. So I wouldn't stress too much on that. Okay, there are a couple other big videos there that are going to help you out a lot as far as preparation for this experiment, particularly for your final practical. There is a recrystallization video, in fact 2 of them. You do not need to see the Craig tube, so there's one labeled Craig tube. Don't worry about the Craig tube recrystallization, we won't have to do that one. Okay, so that one unfortunately doesn't have any audio, so you just get to kind of read through the procedure while you watch me recrystallize a solid. Okay. If you haven't done a filtration before, if you've done Gen Chem at Mesa, they made you do a filtration system already. We have a very similar setup for our labs. You'll end up doing that again next week. But there's a video online explaining what's going on with the filtration, the different parts of it, to make sure that you understand what's happening with it. So I recommend that you watch those 3 videos so that you're comfortable with the actual techniques, so that when you get to the practical, you actually know how to do them. Okay. The goal of this video was to get you set up with the overall theory behind it so that you don't miss any questions based on it. Okay. I believe that is the end of the video. Oh, shucks. I want to go back to this technique here real quickly for the recrystallization, because I did forget one kind of important aspect. Okay, when we go through and try to dissolve the compound, okay, and this is a good question for quizzes, hint, hint, hint. Okay, so pay attention to this. How much solvent do we add? Okay, and this is where it gets kind of tricky. Solubility is dependent on several things. Okay, it is dependent on intermolecular forces, which we saw, but it's also dependent on amounts. If I take sand and try and dissolve it in water, it doesn't dissolve. Okay. However, if I take sand and throw it into the ocean, sure looks like it dissolves. Okay. So our abilities to get product out of a solvent are really dependent on how much solvent we go through and use. If I use a lot of solvent, that solvent increases its likelihood of breaking apart those intermolecular forces and reducing my yield. Sometimes reducing it to the point where I can't get any crystals back. Okay? So one of the trickiest parts of the recrystallization procedure is knowing how much solvent to use. Okay? So let's address that issue here. You ready for the magic number? Okay, it's always frustrating for students. They don't really like this answer, but it is the absolute correct answer. Okay, so first off, we want to specify its temperature. Okay, we want to use hot solvent, because if we use cold solvent, it's going to take a lot more solvent to dissolve it. So we'll stick with the hot. Okay, and for every gram of compound you're trying to dissolve, it's going to require exactly enough solvent to dissolve it. Okay, yeah, and you thought I was going to give you a number. Haha. There is no magic number. Okay, the only way we can get you a magic number is if it's done 1,000 times over and we figure out exactly how much to go through and do, and then we insist that you measure out exactly that much. Okay, the odds that that's ever going to happen, really, really, really slim. Whenever you see a recrystallization procedure, it's hot solvent and just barely enough to get it to dissolve. Okay, so it needs to be kind of a slow process. Slowly add the solvent, let it dissolve a little bit. If it doesn't look like it's dissolving, add a little bit more, until eventually you decide, oh, it's all dissolved. Take it off the heat and let it cool down. Okay, I know that's a bit frustrating. It's not a hard, fast answer, but that's the way recrystallization works. Okay, just kind of be aware of that. If you've got questions about it, please feel free to ask me in class. Next week, I should be there. Other than that, I think we're good. So I will see you next week. Have a good weekend.